Hello everyone, welcome back to Master Electronics. 7 episodes. Setting up a Linux machine, downloading 250 GB of source code, understanding what is inside it, learning how the build works, running a build that took 7 hours to finish. All of that work produces one file. This 15 GB image right here. And right now it is just sitting on a hard drive. It means nothing until we put it on hardware. In this episode, we changed that. We flash this image to an SD card, slot it into Raspberry Pi 4, power it on, and watch Android 14 boot from source code that we downloaded and compiled ourselves. Let's do it. The full hardware setup, the Raspberry Pi 4, the fan cooler, the micro HDMI adapter, the HDMI to VGA cable, all of that was covered in episode 1. If you have not seen it, please go watch that first. Link is in the description. For this episode specifically, 3 things to note that were not relevant before. First, SD card size. Use at least 32 GB. The Android image is 15 GB and Balena Etcher will reject a 16 GB card with an insufficient space error. I am using 64 GB. Second, micro HDMI port 0. The Raspberry Pi 4 has two micro HDMI ports. Use the one closest to the USB-C connector, that is port 0. Port 1 gives no display output on this build. The Raspberry Vanilla AOSP configures HDMI 0 only in the device tree and display hall. Port 1 simply receives no signal, nothing wrong, just not configured. Third, the USB-C port is dual purpose. It is both power input and ADB connection. When I want to use ADB, I connect the USB-C cable to my laptop. The laptop provides power and ADB over the same cable simultaneously. That is everything you need to know before we start. Let's flash. One more thing, you will need a USB mouse to navigate the Android UI as we are not using touchscreen. To flash the image, we are using Balena Etcher. It is a free open source GUI application built specifically for writing OS images to SD cards and USB drives. I downloaded it from etcherbalena.io. Link is available in the description below. It is available for Windows, Mac OS, and Linux. Why Etcher instead of the dd terminal command? Two reasons. First, Etcher automatically detects removable drives and excludes your internal drive from the selection. That safety net matters when you are writing 15 GB and one wrong device selection destroys data. Second, it verifies the write after it finishes. It reads the data back from the SD card and confirms it matches the original image. With DD, you have to do that manually. 3 steps. That is all Etcher needs. Select image, select target, flash. Let me show you. Step 1. Select the image. Click Flash from File and navigate to the image we built. There it is, Raspberry Vanilla AOSP 14 image, 15 GB, the entire Android 14 system for the Raspberry Pi 4. Step 2. Select the target. HS scans for removable drives and lists them here. Your SD card appears with its size 64 GB in this case. Notice, your internal drive is not in this list. HR keeps it hidden for safety. Step 3. Flash. HR is now writing 15 GB to the SD card. Expect 5 to 15 minutes depending on your SD card and reader speed. After writing, HR automatically runs a verification pass. It reads the data back from the card and confirms it matches the image. If verification passes, the write is confirmed good. Now flash is completed. Android 14 is on the SD card. Remove it from the reader. Time to move to the hardware. Now the physical setup. This is straightforward. Insert the SD card into the microSD slot on the underside of the Raspberry Pi 4. Connect your display cable to micro HDMI port 0. That is the port closest to the USB-C power connector. I am using a micro HDMI to HDMI adapter into an HDMI to VGA cable that works fine. Again, port 0 only. Port 1 gives no display on this build. The Raspberry Vanilla AOSP configures HDMI 0 as the only display output in its device tree. Port 1 is not a bug, it is just not configured for this build. Plug in a USB mouse, we will need it to navigate the Android UI. Make sure the monitor is powered on. We want to catch the very first frame of boot. For power, connect the USB-C cable to your power supply or to your laptop. Remember, if you want to use ADB at the same time, connect it to your laptop. The laptop provides power and ADB over the same cable. If you are just booting to check the display, any USB-C power source works. A phone charger will show a low power warning on screen. That is normal. A proper 5V 3A supply eliminates it. The Raspberry Pi 4 has no power switch. Plugging in the USB-C cable is how you power it on. The screen is blank for a few seconds while the Pi firmware initializes. On this build, the display does not show bootloader text or kernel messages. The Pi firmware and kernel are running silently in the background, initializing the CPU, memory, storage, and all hardware drivers. You will not see any of that. The first thing that appears on screen is the Android boot animation. There it is. That is the Android boot animation. The Linux kernel has finished starting. The RAN disk init ran, mounted the system and vendor partitions, handed off to the Android init. And now Android init has launched the Surface Furniture graphics stack, which is drawing this animation to the screen. That is the Raspberry Pi's GPU, the video core rendering an Android UI on hardware we built from source. The boot animation plays while the rest of the Android starts in the background. System server is launching. Services are initializing. The package manager is scanning the installed apps. Zygote is starting. It will be the parent of every app process. We will go through all of this in detail in the next episode. Episode 9 is entirely about the Android boot sequence. For now, just appreciate what is happening on screen. Android 14 is running on a Raspberry Pi 4, built entirely from source code. Let me show you what we have got. This is the Android open source project, the same code base that Google uses to build every Android release compiled on our machine for this specific hardware. Let me open settings and show you build information. Android version 14. Build number AP2A 240905003. The exact build ID we selected with lunch in episode 7. Model AOSP RPI4. That is the target product we set. This is not a coincidence. Every one of these values came from something we configured during the build. The lunch command set target product, target build variant, and build ID. And those values are now displayed on a running Android device. It is a real Android, not a demo, not a simulation. Now let me connect ADB and show you something even more interesting. Let me connect to it over ADB. The USB-C port on the Raspberry Pi 4 is dual purpose. It is the power input and it is the ADB connection. Disconnect it from the power supply and connect the same cable to your Ubuntu machine. The laptop now provides power while the ADB connects over the same USB connection. There it is, our Pi showing up as an ADB device. AOSP RPI4, the product we built. Android 14. And this is proof, it is all real. ARC64 64-bit ARM running on the Raspberry Pi 4's Cortex A72 processor. The bootloader, the kernel, the Android framework all started silently before the first frame of the boot animation appeared on screen. We are in. We have a shell on an Android device that we built from source and flashed ourselves. This is a starting point for everything that comes next in this series. Every episode from here, modifying the framework, adding services, changing system behavior starts with a working device exactly like this. Let me quickly recap what we did in this episode. We flashed the 15 GB Android image to an SD card using Balena Etcher. We connected the Raspberry Pi, powered it on, and watched it go from blank screen to Android boot animation to launcher. We verified it in settings Android 14, build, AP2A 240905003, and we connected over ADB to confirm it is a real running Android system. That is 8 episodes, from nothing to a running Android device built entirely from source. Now the real work begins. In episode 9, we go back to what we just watched on screen, the boot sequence, and we actually understand what is happening at each step. Bootloader, Linux kernel, init, zygote, system server, launcher. We look at the source code behind each stage. We use ADB Locket to see the real boot logs. And we understand the chain of events that takes a powered off piece of hardware and turns it into a running Android system. If this video was useful, please like the video and subscribe to Must Electronics.